Well, we're nearly there. Welcome back, everyone. And it's official. Well, this is going to be our last class meeting. Congratulations, everyone, on getting through the semester. I know you all probably have other classes, and this is just one class on a big pile of other workloads and responsibilities you're getting through. But for this class, it's not meant to be torture getting through the final exam. The final exam is kind of in the spirit of a final project, but a project's kind of tough when it's two classes, one fully online, one in person. And so what I did was pretty much just made a parallel set of problems here from the final exam review. Both documents here on the final exam review and the real final exam have been completely randomized. And our goal is really just to go through the statistical methods of the course. So these are all the tabs I pulled out just going through the Canvas course page. When you're solving the final exam, use Canvas as one big resource. You've got everything you need there. There's going to be the conditions, the formulas, the syntax for RStudio, anything you could use about coming up with what do you have to say to set up the hypotheses? What do you have to say for making the right conclusions? All included. So think of this last project here as kind of a glorified homework assignment where we're choosing the right statistical method, cite this document as needed to know what method you have to use. It is a take-home exam, so we have to work alone. I can't tell you how to solve each one of these problems, unlike the homework assignments. But just like the homework assignments, we're also using RStudio, real industry software, for cranking out some of the data. And if you run into any errors, say maybe you're doing a histogram or a box plot or side-by-side box plots for the ANOVA methods, if you're running into any errors running your chi-squared methods, your t methods, anything along those lines, send me a screenshot of your syntax or even just copy and paste it directly into an email or message in Canvas at any time. And there's no secrets about using RStudio. I'll always help you work through that code. If we can't figure out how to say create the histogram, I'll just send you a screenshot of the histogram so you can include it in your overall document and then work on it through the conditions. So any issues that come up, once again, don't hesitate to ask about RStudio. I can't tell you how to solve each problem. I can't say what method you're going to use on a problem by problem basis. But if you kind of copy what we did on our final exam review, where we've selected the method on every single problem, you'll get some really great ideas on how to start them out. And again, we're going to assign this final exam just on the last 15 minutes of class today. So we may not fully analyze every single problem on our review. We've pre-analyzed all problems to say what method fits what. And after I complete grading for all my classes on Friday, it's kind of busy for me too, I'm going to be turning over to working on solving all the problems there as well for one extra final resource. So that's our goal for today. Any questions or comments at all, folks, before we start? Okay, well, let's begin. I'm glad that you folks made it in here today. For people who are watching the recording later on, if you have any questions that come up, don't hesitate to ask. And same for everyone here today. Don't hesitate to pump the brakes at any time. If there's a problem you'd like to see done before the one we're working on, after the one we're working on, for example, if you want to do exercise 6 before we go to problem number 2, don't hesitate to interject at any point. Otherwise, I'm probably just going to go in order of the problems we have there. They're randomized anyways. Keep in mind, there's also 2 extra credit opportunities if you haven't gotten to them. One is to do the course evaluation. Send me a quick email that you've completed it. And I'll drop 3 of your lowest homework assignments at the end of the semester, which is substantial because we have a total of 12. So your homework grade should come out pretty high once you're caught up complete with the homework. Usually that's a high grade in this class. And if you are behind on any assignment, that's the last day for any submission. But let's jump back in. Here's where we left off. We pre-analyzed all these data. These screenshots that you see here are from the file, choosing a statistical method where we just indicate which method we're using. On the real exam, every problem is asking you to perform a complete analysis, but be very mindful of instructions. If it says confidence interval, we really have to do the confidence interval analysis. If it says at 90% confidence, that's the expectation. So There's also, just like we did on the homework problems and the lecture notes, a kind of a structure, a guide, a skeleton of state, plan, solve, conclude. I put that on the real exam, but I kind of neglected it to do it on this document. I think I just kind of slapped these questions kind of fast together over the weekend. So let's just write this out as we go. For the state portion of the complete analysis, all I'm asking you to do is indicate what the practical question is. Directly cite it out of the problem, write it in your own words. It's up to you. It's my way to kind of help us all think about the context again and drive us to the right conclusion. So in the interest of time, to solve as many problems as possible, I'm going to cite the direct practical question requiring a statistical analysis right out of the problem, probably most of the time. So we read through these data, historical variables, regular aspirin use. The other variable was deaths due to cancer. We're told, let's see here, let's read through this again. Out of 549 study participants who regularly used aspirin after being diagnosed with colorectal cancer, there were 81 colorectal cancer specific deaths. So let's start with that information there. So there are two variables. The role of one variable, regular use of aspirin, is to split our populations into two independent populations. First population had a sample size N1 equals 549. Deaths to this is two outcomes, but we indicated the success for this is going to be specifically dying due to that particular form of cancer, because that's what the study is concerned about. That's what it's studying, deaths to the cancer. So we say X1, the number of successes in the sample is 81. So the statistic P hat 1 is take the successes 81, divide by the sample size 549. So that's our first proportion. I remember this was kind of tricky on exam 3, so let's go carefully. I think this is a good review problem. For the other population, it was those that did not regularly use aspirin. So it says, whereas 730 similarly diagnosed individuals who did not regularly subsequently use aspirin, that was a bad circle, but let's go with it. There's 141 cancer-specific deaths. So let's call that the second sample, N2. 730 participants in that study. The successes, 141. So the sample's proportion of successes, just like before, we call p hats 2, is 141 over 730. So after determining the method, read through the context again like we're doing. Try to pick out these elements that you know are going to come back in the formulas later on. And now we can start going on the next phase of the process. Any questions so far, folks, with getting through the state, summarizing the outcomes? Okay, now off to the planning phase. If it's a confidence interval, we're not stating hypotheses whatsoever, but the thing that's the same for this test is if there's two statistics, you will have two parameters, so we must define them. Let's begin by saying let P1 and P2 denote it's not the sample's proportion of successes like we have here. This is going to be the population proportion. We can't say successes. We have to say what the successes are in context. So we'll say proportion of colorectal cancer specific deaths for all people. At this point, we're saying what the population is. Our categorical variable here, the first one, is saying what the population is. All people who were diagnosed, who had regular aspirin use, or did not. So those are the two outcomes. So let's say all people diagnosed with this cancer that regularly, that was a hard word, used aspirin or did not, respectively. So now we've set up a one-to-one correspondence. The first population that came up is going to be relative to the parameter P1. So that's going to be the true proportion or true percentage of all deaths for people who were diagnosed with colorectal cancer and regularly used aspirin. Likewise, for P2, this is for those who did not regularly use aspirin. Well, that's sometimes the tricky portion of the planning. Because it's a confidence interval, we're just moving on to the next conditions. But any questions or comments at the moment? Okay, now onto the solving phase. This is split into two. Part one, and again, I have a skeleton, state plan, solve the specific instructions on the real exam problems. But here we're studying them individually. Let's write this out. Part one is to check conditions. First thing we're looking for, we need to look at this context again, is if we have any information about randomization. Doesn't say much, does it? This is a one really short paragraph. It just says out of 549 participants, 730 similarly diagnosed individuals, but it doesn't say anything specifically about randomization whatsoever here. The sample could have been randomly selected. The authors of the study might have really great reasons to say it's a representative sample, but no information given just means here, we'll just say it is not known. If the sample was random. So that doesn't mean we stop the procedure. This is something we can mention in our overall conclusion at the end. If you didn't mention that our results could be challenged due to the randomization issue, I'm not going to be super ultra picky on your conclusion, but that would be one unknown about this. Next thing we're going to look into is if the sample sizes N1 and 2 are large enough. They look plenty large, but that's no guarantee when we're looking into categorical data if they're actually large enough. And this is actually really quite tricky. If it's one proportion, two proportion, a hypothesis test, or a confidence interval, you probably notice that the condition checking changes a lot on a problem by problem basis. So here's where you have to do a little bit of extra research on your part. Go look up the method on the Canvas page or in the textbook. I have it pulled up here. We are in chapter 20. Look for the confidence interval procedure specifically. And here, this is where we know for sure if we're on the right track. We're looking for successes and failures in the sample, and the cutoff is 10 for both in both samples. So going back, just like with the homework problems, we need to cite those numbers. So let's say this in line on the document. For the first sample, we had 81 successes, which is exceeding 10. And for the failures, take 81 minus 549. Let me just do that really rapidly here. Giving us 468 failures. So we're definitely on the right track, but on your exam for full credit, definitely show these counts. I forgot to say greater than or equal to 10 here. Let me clear that off. Greater than or equal to 10 failures. And for the second sample, pretty good shape here as well. Lots of successes. 141 greater than or equal to 10 successes. And back to the calculator. It's been a long semester, and when you're tired, arithmetic is the first thing to go. So let me do this as accurately as possible. 730 minus 141 is 589. Greater than or equal to 10, failures. So all of our benchmarks are met. I put in greater than or equal to 10. That was our condition we had to pass. If just one of these four fails, conditions are not met for these data. So here we can now say the sample size is large enough. That means we can move forward on part 2. The instructions are pretty much just going to say, if it's a confidence interval, construct the interval. Okay, any questions at the moment before we get to the mathy side of this? Okay, on to the next part. As far as constructing the confidence interval goes, first thing we want is the statistics, but we have them ready to go down below here in the screenshot. Next thing we want is this standard error. Let's make that maybe our first thing to take a look into. Standard error of p hat 1 minus p hat 2 is going to be, we want to be really careful with these kind of equations because sometimes it's the standard deviation. The standard error formula also changes a lot from chapter to chapter, situation to situation. So after writing it down, good idea to double check. Let's put this down carefully. P hat 1 times 1 minus p hat 1 over n1 plus p hat 2 times 1 minus p hat 2 over n2. And if I was taking my own final exam, I definitely would go back to chapter 20, look that up and just double check, because let's emphasize something. If this was a hypothesis test, notice what you calculate instead. Completely different formula, and in fact, a different statistic. We use the pooled sample proportion, but we do none of that if it's a confidence interval. So again, a lot of this is up to your own research, looking up the methods, but this is par for the course for what we do in statistics. No one is going to try to remember every single statistical method. What you do is you get faced with a new problem, you analyze the variables, you see how the samples look, and then you look up the methods. So that's what you're going to be doing as an experience on the final exam. You're expected to look this up, carefully check, make sure the right corresponding formulas match the situation. But once we have this in place, all it is now a math problem. So we're going to throw in, I'll put this on the notes just for the sake of a paper trail. This is worth partial credit too. So if something goes terribly wrong on the calculator, I would give good partial credit for just this step. Cite the statistics, put in 81, 549 times 1 minus 81, 549, over sample size, 549, plus, and then do it all over again for the second statistic, 141, over 730, 1 minus 141 over 730, divide by 730. So this is pretty much the major part of constructing this confidence interval, running through the standard error. Back into the calculator. This would go in, obeying order of operations in this kind of way. SQRT for square root, 81, 549. Put in the literal times there if you're using this as a calculator, our studio. They go 1 minus 81, 549. Divide by 549. And now it's halfway done. Okay, just double checking the numbers. It's easy to transpose a digit. Do it again, 141 over 549 times 1 minus 141 Hang on, that's a mistake. That's over 730. That's right where the red dot was. Can't believe I missed that. Times 1 minus 141 over 730. Divide by 730. And there's our standard error. Typical accuracy here is go for something like 5 significant digits and you'll be in good shape. So I'll carry in a 0.02104. I mean, that's not quite 5 significant digits. Maybe let's go a little bit further. 0.021038, a little bit more accurate. Okay, we've got 5 significant digits, which is a good idea for, say, your test statistic. Once we have the standard error, we're basically done. We're going to start just putting things together. Next thing we usually put down on paper is going to be Z-star. You can compute this fresh, or you could cite, say, chapter 19 has a great table for critical numbers somewhere. There it is. We're at 90% confidence, so you're just fine to cite this, or rerun the syntax if you want more accuracy. But for a critical number, 5 significant digits is pretty common. 1.6449 will do the job. Last, we use the statistics, but again, they were already here on paper, ready to go. And now we're just stitching this all together. To estimate the difference in population proportions, P1 minus P2, we put in the point estimate, P hat 1 minus P hat 2. Add or subtract some critical number Z star and multiply that against the standard error of P hat 1 minus P hat 2. So nearly there. This boils down to just making a whole bunch of substitutions. 81 over 549 minus 141 over 730. Add or subtract our wonderful critical number, 1.6449, multiply 0.021038. So this is the nuts and bolts of the method. Now going back to the parameters, it's a good idea to remind yourself what you're calculating when you get beyond this step, cranking it out fully. You're calculating the difference in population proportions. So we go from the statistic, the p hats, to the original parameters. These are going to be constrained between two values, a lower bound and an upper bound. And one fast computation is essentially going to give us both. So take 81 over 549 minus 141 over 730. I'll go for lower bound, so minus 1.6449 times 0.021038. So here's our lower bound. We get a negative value. At this point, we're going to round maybe a little bit less severely. 4 decimal places is not a bad choice because these are, in fact, percentages, really, just written as a proportion. So take negative 0.0802. Then do it again, hit the up arrow. Most calculators will support re-entry here. Swap to positive, and that's our upper bound. Notice it's negative on both ends, so that says something about the study. So negative 0.0110. Good idea to double check all these digits. And penmanship as well, that looks like the number 6. At this stage, for the conclude step, I'm going to solve for one of the parameters. I'm going to keep P1 right where it is. If we see our guide up above, P1 is regular aspirin use. So keeping P1 exactly where it is, it looks weird because we're looking at negatives and we're dealing with proportions, but when you're subtracting proportions, that's absolutely appropriate. Negatives can occur. So we'll have P2 minus 0.08 O2, P2 here, minus 0.0110. I think I might have misspoke when I said this step, where I'm just adding, not subtracting, adding P2 to all three sides of the interval, giving us this last interval here. At this stage, the final phase of giving a complete analysis of this data is to directly interpret the confidence interval. So we'll use the plan phase. Not a bad idea to go back to the statements phase as well. But one thing we've emphasized all semester as we were solving our problems, the way homework problems were graded as well, is the emphasis is to directly interpret your interval that you have. Then go back here, make sure that you really address that practical question. We can directly answer it, but the grading is more about saying exactly what this means in practical terms using the context of the study. So here's our conclusion. We did a 90% confidence interval on this one. So we'll say with 90% confidence, we're going to first define what P was in the study. This is going to be the population proportion of colorectal cancer specific deaths for all people diagnosed with that cancer that regularly used aspirin. So let's say that carefully. The population proportion of colorectal cancer specific deaths for all people diagnosed with this cancer that regularly used aspirin. Okay, so that made my hand tired, but we're ready to go back to the interval. We read out what P1 is, and now we can say is from this proportion lower to this proportion lower, then the same group of people that P2 did not use aspirin regularly. So let's write this in as is from. You could write this as a percentage if you prefer, 8.02%. You probably want to change that word to percent to keep it completely parallel. So I'll keep mine as a proportion. Is from 0.0802 lower. When I say lower, I've conveyed the negative sign, so we don't want to duplicate that, to 0.0110 lower than similarly diagnosed people. We're returning to blue because now we're putting P2 there. We don't have to say the entire thing again because that's one big long run-on paragraph. So I just paraphrased to similarly diagnosed people that did not regularly use aspirin. So this is where I'm going to paying the most attention when it comes to grading. This is where we kind of hyper-focused on grading homework assignments, writing down our solutions. If it's a hypothesis test, we have to directly interpret that we found evidence the alternative hypothesis is true, or that we failed to find evidence that the alternative hypothesis is true. And if you want, again, it's not a bad idea to go back to the statement phase, make a follow-up comment. It's not strictly required. It's good practice. But don't forget this part. This is the major portion of the credit on the problem. So I'll put this in orange to convey this is just wrapping this up. Does the data suggest regular use of aspirin after diagnosis will decrease the incidence rate of the colorectal cancer specific deaths? We can say yes, because 0 is not in this interval. Those that used aspirin regularly always had a lower rate of deaths. So we can say now for our final comment, yes, regular, yes would be weird there. Let me just say it this way. Regular aspirin use appears to reduce the death rate for this cancer. Again, it's in orange because it's just an additional comment. If you leave it off, I wouldn't consider that a big deal. It's best practice to readdress your statement phase question here. But this is where the major credit is in the conclusion. For all confidence intervals, similarly, if it's a hypothesis test, we have to directly go back to whatever you said the alternative was, what your parameters were. Well, they're kind of long problems, mainly because we're talking through them. If you are a well-prepared student, the final exam shouldn't take too long. It's 7 problems. My advice is to chip away at it day by day. You could possibly have this complete before final exams begin. Final exam week begins. But that's one down. Any last questions at all, folks, before we go to the next problem? Okay, so on to the next. This was kind of an interesting problem where people did something sketchy. They took a class of children who failed the mathematics part of the City University of New York skills assessment. And they went basically to summer school to get some extra practice, retake that test. So this is their scores on that specific mathematics assessment test for the City of New York. These are the scores after they took the test. But the weird kind of shady thing they did, it's kind of amazing they got away with this. The parents might have signed a release, who knows? They flashed subliminal messages in front of these children while they were in their summer program designed to raise their math skills. Again, if I found out people were running an experiment on me when I was just trying to raise my skill in anything, I'd probably be a little bit upset. But they really did this study. And these were the messages. The positive one were each day I'm getting better at math. So that doesn't sound bad. I'm not sure what's going on with this highlighting anymore. Let's undo that. The neutral message was people are walking on the street, and I don't think that would offend anyone. So they didn't have a negative message at least. So it wasn't the worst unethical thing we've ever seen. What we want to do is analyze these data. And this one was a tricky one to come up with the analysis for because there's absolutely a categorical variable here that has 2 outcomes. It's message. But there's truly one quantitative variable that we're going to analyze. Sure, there's a quantitative variable here, the before group, a quantitative variable here, the after group, but the data is dependent. Each before and after is on the same subject. So what we're going to do, much like we did in a homework problem, is compute the difference between these data, and we're going to do an analysis on the change in score, the difference before minus after. So let's say that here on the notes, we're going to analyze. Let's give a name to this new variable. Most of them improved. I think maybe even all of them. I'm not too sure eyeballing this data. I think they all improved. So I'm just going to call this improvement. That's going to be our variable defined to be after minus before. If you went before minus after, completely fine. Your analysis is going to look a little bit different. Your setup for the hypotheses will look a little bit different, but your test statistic is identical. Your p-value, well, the sign of the test statistic is different, but your p-value is identical. Your conclusion is the same. I'm going this way just to make positive values. Just feels a little bit more straightforward going in that direction. So this time, it's complete analysis using a hypothesis test. And this is kind of a hard problem to visualize because the data set in the middle kind of takes up a lot of real estate here. So let me put down just a quick screenshot. And let's start off our complete analysis with the statement phase as before. we want to state the practical question in this problem. And it was all about the subliminal message. It wasn't about if the raw improvement was above a certain amount. We want to know if there is a change, a greater improvement in math scores for the positive message versus the neutral message. So let's say it this way. Did the students that were exposed to the positive subliminal message which was each day I'm getting better at math. Or, when you think about it, if you join the Zoom session, there's a subliminal message there. The password is math is fun. So that was an unintentional subliminal message, but it was positive. So no harm done there. So did students that were exposed to the positive subliminal message improve more on the math assessment? This is the New York State math assessment, but I'm going to just abbreviate this whole thing to math assessment. I'll leave the context fully defined up here in the body of the problem. So say, did the students that were exposed to the positive subliminal message improve more on the math assessment than those exposed to the neutral message? Although it's not required, it's a good call to add just a little bit more to this as a reminder on your conclusion. We're not talking about individuals here. We're talking about averages of all these students that might potentially take the test. So let's say it here, on average. So that's our state phase. Next, we're going to go off into the planning phase. Because we're doing a complete analysis, we need to state both parameters on this one and state both a null and alternative hypothesis. I think I need a better screenshot. There's a little bit more to this context that I definitely want to capture. So let's go screenshot to this much. But that's the practical question of this problem. Again, you could directly cite it right out of the body of the problem, especially if you see a question mark. That's kind of a giveaway. This is the research question right here. But any questions at all before we go to the planning portion? Okay, so let me look at this context again. It said 18 students who failed the mathematics part of the City University of New York skills. That means for some reason, when I read this problem, I thought these were children, but these look like they are university students. So they are probably all adults, unless some of them is an early college student. Assessment that were randomly assigned to receive either positive message or neutral message. So with that context in mind, let's say the data is quantitative this time, and we're talking about averages. So we're going to use mu's this time. Let mu1 and mu2 denote, say, either mean or average, up to you. I'll go with the statistic standard description. Denote the mean. You could say population mean, true mean, or just say the mean like this, but definitely say what the population is. So let's say the mean for all students. And they had to specifically take the City University of New York skills. So let's roll that into the context. We're not talking about all university students in even New York. We're talking about that particular demographic of students. So I'll say for all students that take the City University of New York And I'll just say math assessment to abbreviate the rest. Okay, so that's the population. And I forgot one word there. Oh, darn it. I don't think I can squeeze it in. Let me make sure that this is in because this is something that I do look for, that I've taken off points before. It's an easy mistake to make, but when you say the mean, you have to say the mean of what? Much like when you're talking about proportions and its successes, failures, you have to say what the successes are. This was the mean improvement in the math assessment So it's a score, it's how much they improved on average. So don't forget that part. If you say mean, you have to say mean of what? Maybe it's the mean height or the mean amount of time. Here it's the mean improvement in the math assessment. And let's just say here to be specific, score. So we're talking about point values on an exam. Now let's get into the population for all students. That take the back to this part of the context, city, University of New York, skills assessment. All right, I'll just say again, math assessment. And they took a summer program. They're exposed to subliminal messages. So let's paraphrase that by saying, and were exposed to positive or negative subliminal message, respectively. The respectively grammatical structure is helpful here because this is a long sentence already. We don't necessarily want to say it twice for each of the parameters. With our correspondence saying respectively as a grammatical structure, mu1 is now the average improvement in scores for the positive subliminal message, and mu2 is the same for the neutral message. I think this is a tough set of parameters to put down on paper. Any questions at all, folks, getting them both on? Okay, next up, because it's a hypothesis test, we're expected to state both a null and alternative hypothesis. So let's say it here. I think let's go to a new page. Test. The null hypothesis are dealing with the difference in means for our procedures. So the null is that mu1 minus mu2 equals 0. And some people have asked, you can also say mu1 equals mu2. It's mathematically 100% consistent, more of a stylistic choice on how you decide to format. So that's our null against the alternative. Big trick on writing out an alternative hypothesis is oftentimes if there's a question mark in your problem, that's the research question, which is the alternative hypothesis. So let's go back to that statement. Is there good evidence that a positive message brought about a greater improvement in math scores than the neutral message? The word that jumps at me the most is this: greater improvement. That means it's not a two-tailed test. This is a single direction. Greater improvement in this situation would mean mu1 is the positive subliminal message. It's larger. So you could write mu1 minus mu2 greater than 0. Mu1 is larger than the difference between is positive. So a right-tailed test on this one. We'll test at, it didn't say what the significance level was in this problem. When we encountered this on the homework, occasionally you had to come up with your own significance level. On the final exam, I decided to just be definite on all of them. I stated a significance level on all the hypothesis tests. But for this one, we'll choose our own. It's about subliminal messages. So anything that has to do with something wonky in psychology, I feel like minimizing a type 1 error is not a bad call. So I would personally make alpha equals 0.01. But that's my personal preference on that one. So that finalizes the planning phase. Now for the solving phase, first we're checking conditions, and we must support conclusions with displays of the data. I wrote that in as a statement on the final exam for the quantitative problems, just so that we don't forget. There's an expectation when we look into data for quantitative, we're going to either provide a histogram. One histogram might do the job. So even though it says displays, it's depending on the situation, one might work. But for this context, if we have two independent populations, we're looking into two displays of data. We have to look at how the analysis for the improvement looks in terms of skewness outliers for the positive group and the neutral group independently. So at this stage, we're now going to use RStudio a little bit more heavily to support our analysis, getting those graphics. Any questions at the moment before we take a look into the condition checking? Okay, let's run through it. Condition checking with categorical is usually a little bit more straightforward, but for quantitative, it's touchy. So we need to visualize the data. At this point, we need to import. Like on the real final exam or on the review, I'll have text files like you see here, entitled this kind of way for the right problem. Here's the problem 2 file. It's normal, so it's imports just as we see it. Usually we click away the view. And now for dealing with these data, these data are a little bit trickier. It's kind of like the kind of way the data was formatted for chi-squared. This is one stacked. It's not separated into before, after for positive and for neutral. We just have a categorical variable column, a before column, and an after column. So analyzing these data is going to go like this. First thing I'd probably want to do is separate out the categories. Let's go for, we're doing before, after minus before, so a difference in the scores. But I want to do after minus before for all the positive. Let's go here, and then do it again for all the neutral. So we have to use our subsetting trick once again, like we did for ANOVA. And again, this is the side of the work here where if you encounter any problems, if it's giving you any syntax errors, or you're not sure how to run the syntax on getting the histogram, send me a quick email, message through Canvas, and I'll help you out right away. So let's get started. First thing we want to do is separate out variables. I'll call this one positive. It's going to be a difference in after minus before. So I'll cite problem 2. Probably should have given that better name. So, but let's go with what we have here. Problem 2, select after. But if I do it like that, I'm selecting after for everybody, both in the positive group and the neutral group simultaneously. So I want to subset into just the positives. I'm sure you could do this all by hand, but that is tedious, busy work. Making RStudio do this, it can take a few moments, save us minutes of our valuable time during finals week, possibly dozens of minutes. So go after minus before, and here, before we go into the minus before, we want to also say, this is going to be specifically for, go to the data frame problem 2, select message, and we want that message to be strictly Verbatim as you see it here by the red dot, positive. Equals, we're making a comparison, put in quotes, match the case, positive. Then let's run this to just make sure it actually runs. I have a string of values, 24, 25, 33, 29. Those are the right values. And there's only 10 of them because there's only 10 people in the positive group. Okay, so we've got that, but then we're going to go minus. Let me hit enter so we can see it all in one line. Rewrite this whole thing. Well, maybe let's start from scratch. Let's go problem 2. $. Now we're subtracting the before, the way we indicate we're subtracting. Then go a bracket here to subset in, problem 2. $, select the message. Make a comparison check, make it exactly equal to. Should look just like that, neutral. So now it's going to form the pairwise differences. Let's run this, see what we get. I have 6, 1, 13, 11. 24 minus 18 is definitely 6. But hang on. No, I subtract this in a weird way. Sorry, this should have been positive on both. Let me try again. So if I run that and then hit, or I should look at my warnings, longer object length is not a multiple of the shorter object length. Hang on, I think I have to debug my code on this. Let me see what's going wrong. Problem 2 message is positive. Let me comment this out just to see where my error might be. Okay, that part worked there. So I have a problem on this statement. Problem 2. I'm going before, so I'm selecting these. I want the message to be positive again. Weird. I'm not seeing the issue on this. Let me see if I can start over on this line. So we have this. I want to do subtract. Then let me try going slower. Problem 2. I want to select. We did the after, so now I'm going to before. Now I need to subset into it. Carefully. Before, subset, problem 2. I want to have message just like before. I want to select the positive message. So I'm going to go message, double equals, and let me just copy this in just in case I misspelled something. Okay, let's try this again. Hey, no error. I must have just misspelled something, screwed something up some way, somehow. Again, these things are touchy. If you run into any issues, don't hesitate to email me. We'll work through it together and get it fixed. So let's write this again. Positive. Check our numbers. They are different. 24 minus 18 is 6. Next difference is 7. 25 minus 18, hey, that is 7. So we're on the right track. These are the right values on the last one. 27 minus 17 is 10. Okay, so now we have to do that all over again. But the trick here is select all of it. Copy it down. Call this one neutral. So this will be the improvement in scores before minus after. Over here, we just have to change this tag to neutral. So the nice thing about this is if you get it done once, like doing the standard deviation on ANOVA, we did the same kind of subsetting trick. If you can make it work once, you can make it work for all the other groups. Just change into the other category for the categorical variable. So now for neutral, let's double check this. No error is always a good sign. So let me write out neutral. we have 11, 5, 4. So let's check. First one, 21 minus 18. 29 minus 18 is 11. 29 minus 24 is 5. Yeah, we're on the right track. 19 plus 12 is 31. So the next difference is also 12. So finally, we've got all the data in. Now we're doing the condition checking. We just need to visualize how bad are these histograms for the neutral group and the positive group. So that was a definite chore on getting through this. Now we're going to produce histograms. I think last time we did this, we made these side-by-side histograms. So we put in fancy syntax that went par mf row equals c. I believe this goes number of rows, 1, number of columns, 2. So this is just to get side-by-side histograms. You don't have to do this if you do not prefer. Up to you. Type out hist, positive. And we should, so the X label is going to be improvement or positive message. We might have to shorten that up if it's too long. Go hist, neutral. X label will be improvement or neutral message. And there they are. We have two side-by-side histograms. So standing this out a little bit just to make things fit better. You know, they're not too bad. These are sample size 10 and 8. This one is nice. It's no apparent outliers whatsoever. This one is a little bit more wonky. Definitely looks like it has a slight right skew, but it's not severe. It has missing data in the middle, which is okay. But for sample sizes of 8, you can get some pretty odd shapes. So the skew is not drastic. It's not severe. There's no crazy outliers in these data. So I'd say as far as our robustness conditions go, for the 2 sample T procedures, slightly borderline, but really not that bad. I would say that this would be a pass for the conditions. So that's a lot of work to get started. Because we're running short on time, I just want to also share the syntax of what you would do to get the test. I'll come back here, fill out all the statements, double checking those conditions. We'd want to go back to chapter 18, look into the robustness conditions for the 2 sample procedure, which is here. First, we look into how similar the shapes are. Then we combine both sample sizes. For us, we're 18, so we're in this category. T procedures can be used, except for in the presence of outliers. We saw none, so we're okay there. Strong skewness. We see a little bit of skew, but we don't see strong skewness. It wasn't that bad. So although slightly borderline, I would say that this is a definite pass for these kind of data. I would not say that's strong skewness whatsoever. But once again, we're a little short on time, so I'm going to fill in all those words that we just said verbally when I go back to fully solve all the problems on these notes. Last thing I want to share with the context or with the syntax is running the test. So as far as the test goes, you just do t.test, put in here, positive. That was the differences we painstakingly extracted, but you know, we didn't subtract one by one, so this was worth it. Then neutral, make sure to spell everything verbatim. Here's where it gets a little bit tricky because you have to also check your hypotheses. It is a right tail test, so you have to alert that to RStudio, say alternative. Great trick always is start typing a few words, it's going to auto-complete the right thing. Read what you see in yellow. We have to say equals greater. So go alternative equals, in quotes, greater. And this runs the entire test. So you don't have to break out a calculator like we did with the categorical data. For all quantitative data sets, I have shared the raw data. You can just cite the test. The Welsh 2 sample T test here gives us a test statistic, gives us a p-value. I selected 0.01, so this is non-significant. So you could just restate these, say what the test statistic is, p-value, or screenshot in the procedure. I would encourage only take as much as is relative to your context. Bring this in if you want to interpret a single-sided confidence interval. Inf stands for infinity. Since we're not analyzing that and we never define a single-sided confidence interval, you should just screenshot in this much, or just type in t equals p-value equals, that'd be fine as well. So again, we're kind of short on time, so this one was kind of a rapid run through of methods and syntax. I'm going to come back here, finalize it, make it pretty, say all the words that you would want to say for a problem like this one. But this is pretty much the end of our review before we turn into opening the final exam. There's still 5 more questions to get through. Again, they're kind of long if you're talking through them, explaining everything like we're going, but not that long to do in practice. Any last questions or thoughts at all, folks? Running through the major parts of these analyses. Okay, I'll share what I have so far. After grading, I'm going back into this document on Friday and then just solving these one by one. I said that for basically all of my classes, but I want to start with this class and make this class the priority, mainly because, well, this is the first class I have in the week. And also I've released the exam for this one. So if people want to work on it early, I'm going to try to get this one done as soon as possible after getting caught up on our grading. So let's now turn to releasing the final exam. Kind of exciting in a way. The final exam is right here. Let's give us a moment. We're just going to take a short pause, a mental break where I literally just throw it in. I didn't find a way where I could upload this and have it locked, so I just went with this route, upload it at the end of class. So like before, if you like using the Word files, here they are. You can edit them, space things out differently if you prefer. Like the homework assignments, if you prefer to just print things out, you'll have to send me a separate email or upload separately into Canvas your images for the data distributions, the histograms, and so on. But that'll work just fine, just as with the homework. And be sure, take advantage of RStudio, import the raw data. For all quantitative data sets, looks like problems 2, 3, and 5, you don't have to work so hard cranking out everything by hand. Unless you'd like to. No harm done if you decide to run through the formulas. It's always going to be your choice. If you decide to run through the formulas, you'll have to find the statistics for the quantitative data, means, sample standard deviations, and so on. But now the final exam is considered assigned. It has a due date of May 7th. I said 1 p.m. just because that's what I said for all assignments. But this is considered to be fully on time if I get it on May 7th, Thursday of next week. So just to double check, yeah, looks like it's all there. So you can now access this at this point. I took a lot of time proofreading the work on these, but if you see anything that just looks vague in the wording or something that might just be a typo, let me know. I'll revise it, send a message to the entire class right away. Usually that's pretty rare, but again, if I made any mistakes, I want to correct them right away for everyone. So it's an unusual exam. It's more like a final project for the course. Has a due date of Thursday, May 7th. It is an exam, so unlike the homework problems, we're all expected to work alone on this exam. This has never happened in this class before, but if there's evidence of cheating, I'm required to by my department to follow up on it. It's a horrible process, so be ethical and you'll be in good shape. Now you can cite pretty much anything that's a non-human source. You can cite anything that we did on Canvas, any homework assignment. If you've taken other statistical classes, if you're in a biometry lab, so on and so forth, statistical knowledge you can cite freely. It's definitely open calculator, notes, open textbook. It's open computer, expecting you to use R together with RStudio. And if you have any questions, you can always email me. I'm going to answer absolutely any RStudio related question. There's no secrets with that program. For other questions, I can't necessarily say how to solve each problem. That's going to be up to you, but I can possibly clarify instructions, things along those lines. So here's what it looks like. Just like a review, it's 7 problems, 10 points each. Every problem is asking for a complete analysis, but I put in the structure for each of these just for ease of writing, so we don't have to hand draw these in, checking conditions and being more verbatim of what's needed, test statistic and p-value if it's going to be a hypothesis test. So be sure to follow the instructions in bold. I'll go with the significance level. So if it's a hypothesis test, go for that analysis. Next one is also a hypothesis test. These are randomized with no cherry picking. Another hypothesis test, and here's our confidence interval one. If it's a confidence interval, you'll state the practical question, define the parameter, check conditions, and then this will just say construct a confidence interval. Well, this is pretty much the final exam. On a problem by problem basis, here's what it looks like pretty much. I do want to give just one hint because there's one assignment that, well, one chapter that didn't have a homework assignment, which makes it a little bit extra tricky if you never got feedback on that because there was no homework assignment. It's going to be, let me recall what problem that was, I forgot. It's going to be problem 3. I do want to give one hint on. This one is going to be the analysis of variance method. So again, this is the one that we did in class, a couple examples. Third one, checking conditions specifically. So check the analysis of variance problems that we did there, follow it as a model, particularly example 2, because you're encouraged to import the data and just crank out the analysis of variance table. So that's the big hint on problem number 3, just for the sake of fairness, again, since we didn't have a homework set targeting that particular chapter. Well, that's essentially the entire final exam. Any questions or comments at all, folks, before we call it a day? Okay, well, I appreciate everyone's hard work, whether you're here today, I appreciate you all making it in. And even if you're watching later on, I appreciate everyone's hard work in this course. These kind of courses are sometimes a slog to get through, but I personally had kind of a lot of fun and time with this, talking about statistics. Our major goal was just to see what statistical thinking looks like, how to write out complete results, use real software and industry. So if you know you need to take more statistics later on down the line, a good recommended next class might be experimental design or regression analysis would be great choices. But otherwise, have a great rest of finals week, folks. I hope studying doesn't get too crazy. If later on down the line you have to analyze data and you're not sure where to start, don't hesitate to send an email. I'll be happy to help out. And if I can't help you, I'll just point you in the direction of one of my colleagues that has possibly more knowledge. But take care. I'll see you all later. Yep, have a good one, Kate.